Hello friends, welcome to my fourth lecture on Cauchy type integral equations. So we will be solving Cauchy type integral equation of the second kind. Let us consider the non-homogeneous singular integral equation GS equal to Fs plus lambda times integral 0 to 1 gt dt over t minus s. Let us recall that by this star we mean that we are considering the Cauchy principal value of the integral 0 to 1 gt dt over t minus s. Now in order to solve this singular integral equation, we shall reduce it to a Volterra integral equation. How we do it? Let us see. We will need this identity which we have shown in the last lecture. So integral 0 to u dt upon u minus t raised to power 1 minus alpha t to the power alpha into t minus s equal to pi cot alpha pi over this, and then pi minus pi cosec alpha pi over s minus e to power 1 minus alpha s to the power alpha. So we shall need this identity. Now what we do is, let us define a function phi su as phi su equal to 1 minus u to the power 1 minus alpha s to the power alpha, where 0 is less than s less than u. Phi su equal to 1 over u minus s to the power 1 minus alpha s to the power alpha when 0 is less than s less than u. And let us choose alpha in such a way that minus pi cot alpha pi equal to 1 by lambda, where lambda is the parameter in the given integral equation. Now then phi su is the solution of this equation, minus pi integral 0 to u phi tu dt upon t minus s phi equal to phi su. So minus lambda integral 0 to phi tu dt over t minus s equal to phi su 0 less than s less than u, and when s is greater than u, minus lambda 0 to 0 to u. Phi tu dt over t minus s equal to minus pi cosec alpha pi divided by s minus u to the power 1 minus alpha s to the power alpha u less than s. Now how we are saying this? This follows from the identity. We have seen that integral 0 to u gt upon u minus s to the power 1 minus alpha t to the power alpha t minus s equal to this quantity. So if you choose your alpha like this, minus pi cot alpha pi equal to 1 over lambda, then you use this identity. Then you use this identity for the case 0 less than u less than 1, 0 less than u less than u, then you get this one, this equation, and when you take s to be greater than u, then you get this equation. Now what we do is, let us multiply equation 1 by s. So this is our equation 1. In this equation we are multiplying by s. So we get SGS equal to SFS plus in lambda times integral 0 to 1 SGT dt divided by t minus s. I can also write this as SFS plus lambda times integral 0 to 1 S minus t plus t into gt dt divided by t minus s, which is also equal to SFS plus s minus t we can cancel with t minus s with the negative sign. So, minus lambda 0 to 1 gt dt plus lambda times integral 0 to 1 t gt dt over t minus s. Okay, so let us see. So we multiply equation 1 by s, and then we have this. So lambda times, you can see lambda times integral 0 to 1 t gt dt divided by t minus s equal to sgs minus sfs, and then we write plus c, where c is lambda times integral 0 to 1 gt dt. So we have lambda times integral 0 to 1 t gt dt divided by t minus s is equal to sgs minus sfs plus c, where c is equal to lambda times integral 0 to 1 gt dt. Okay, so this is what we have. Now let us multiply both sides of equation 4, this equation. So this is equation we are getting. So let us multiply both sides of this equation by phi su and integrate from 0 to u. Let us see what we get. The equation is lambda times integral 0 to 1 t gt dt upon t minus s. We multiply by phi su and integrate with respect to u from 0 to u. So we get this lambda times integral 0 to u phi su ds integral 0 to 1 t gt dt upon t minus s equal to integral 0 to u phi su into sgs minus sfs plus cds. Now now let us change the order of integration. So we have, let us see how we change the order of integration. So we have lambda times 0 to u phi su ds 0 to 1 t gt dt divided by t minus s equal to integral 0 to u phi su into sgs minus sfs plus c ds. So we want to change the order of integration in the left hand side. So let us see, t varies from 0 to 1. So this is our so this is t equal to 0, this is t equal to 1. T varies from 0 to 1 and s varies from 0 to u. So this is s axis, this is t axis. S is 0 here, say s is equal to u here. So we are integrating first with respect to t, which means that we are taking a vertical strip in this region. For the vertical strip, t varies from 0 to 1 and vertical strips start from s equal to 0 and end at s equal to u. So s varies from 0 to u. Now we will take a horizontal strip in this region. So when we take a horizontal strip in this region, we shall write the limits of integration for s first. So s varies from 0 to u and t varies from 0 to 1. So, we will have r lambda equal times integral 0 to 1 t gt dt integral 0 to t varies from 0 to 1 and s varies from 0 to u. So, s varies from 0 to u phi su ds divided by t minus s equal to integral 0 to u phi su sgs minus sfs plus c. So, on changing the order of integration, now what we do is the integration with respect to t is broken into two parts from 0 to u and from u to 1. So, we write it as a sum of two integrals, integral over 0 to u t where t varies from 0 to u, and then the other integral where t varies from u to 1. So, we have here minus lambda integral 0 to u t gt dt integral over 0 to u phi su ds over s minus t. We can bring here negative sign outside and write here s minus t. So, we have here minus lambda times this, and then which is equal to integral over right hand side can be written as integral over 0 to u phi su into sgs ds minus integral over 0 to u sfs phi su ds and c times integral over 0 to u phi su ds. Now, we know that integral, let us first evaluate integral over 0 to u phi su ds. So, integral over 0 to u phi su ds is, this is phi su we have assumed to be equal to 1 over u minus s to the power 1 minus alpha into s to the power alpha. This is our 0 to u and ds. As we have done earlier also, you can put here u equal to st. Let us put u equal to say s into t, then we will have du equal to, no, we will have to put we are writing it s minus u. So, we are we are not u minus s, it is not u s minus u. So, this is 1 over u minus s to the power 1 minus alpha s to the power alpha ds. So, we are, let us put s equal to ut. Then this will change to 0 to 1 because s, when s is 0 t is 0, when s is u t is 1, and 1 over u to the power 1 minus alpha 1 minus t to the power 1 minus alpha s to the power alpha will be u to the power alpha t to the power alpha ds will be u dt. So, we will get u dt here, and this will be integral 0 to 1 dt upon t to the power alpha 1 minus t to the power 1 minus alpha, which by gamma, which we can write as t to the power minus alpha 1 minus t to the power alpha minus 1 dt. So, this is integral 0 to 1 t to the power 1 minus alpha minus 1 minus t to the power alpha minus 1 dt. This is beta function 1 minus alpha alpha. So, this is gamma 1 minus alpha gamma 1 minus alpha plus alpha. Gamma 1 is equal to 1, and when alpha lies between 0 and 1, gamma alpha and gamma 1 minus alpha is pi over sine alpha pi. So, we have integral over 0 to u phi su ds is pi over sin alpha pi. Now, let us see how we use equations 2 and 3. What we have is minus lambda integral 0 to u t gt dt integral 0 to u phi su ds over s minus t minus lambda u to 1 t gt dt integral 0 to u phi su ds s minus t ds. Right hand side we have calculated the value of 0 to u phi su ds. So, right hand side is 0 to u s gs phi su ds minus 0 to u s fs phi su ds and then plus c times pi into cosec alpha pi. In the left hand side we will use equations 2 and 3. So, let us see how we use equations 2 and 3. Now, in the equation 2 we have integral over minus lambda 0 to u phi tu dt over t minus s equal to phi su. So, let us interchange s and t here. When you interchange s and t in equation 2, interchanging s and t in equation 2, we will have minus lambda integral 0 to u phi su ds divided by s minus t equal to phi tu when t lies between 0 to u. So, when t lies here between 0 to u, the value of minus lambda into 0 to u phi su ds upon s minus t can be written as phi tu. So, the first term, so thus we have integral 0 to u t gt into phi tu dt. The first term becomes this. Now, let us see the second term. So, in case when s is greater than u, we have this identity. So, let us again change interchange s and t here. So, interchanging s and t we have s and t in equation 3, we get minus lambda phi su du ds divided by s minus t equal to pi cosec alpha pi divided by s minus u. So, t minus u to the power 1 minus alpha t to the power alpha, where u is less than t. So, interchanging s and t in equation 3, interchanging s and t in this equation, we arrive at minus lambda 0 to u phi su ds divided by s minus t equal to pi cosec alpha pi over t minus u to the power 1 minus alpha t to the power alpha when u is less than t, and then we put this value here. We put this value here. So, what we get is second term will become u to 1 t gt and then pi cosic alpha pi divided by t minus u to the power 1 minus alpha t to the power alpha dt, and the right hand side is integral 0 to u s gs phi su ds plus minus integral 0 to u s f s this, and then c times pi cosic alpha pi. Now, let us see this first term and this first term, they cancel. Only change is in the variable of integration. Here we have t, here we have the variable of integration s. So, in a definite integral the variable of integration does not matter. So, this integral has the same value as this integral, and therefore, they cancel out, and so what we get is this equation lambda pi cosic alpha pi integral 0 to 1 t to the power 1 minus alpha. We can write t upon 1 t to the power alpha as t to the power 1 minus alpha gt dt upon t minus u to the power 1 minus alpha dt equal to minus 0 to u s f s phi s u ds plus c pi cosic alpha pi. Now, this integral equation is of Abel type. Let us recall that when we discussed the solution of this Cauchy integral equation, f s equal to integral s to b gt dt upon h t minus h s to the power alpha, where 0 less than alpha less than 1 and s lies between a and b. With h t a monotonically increasing function, we had the solution as this solution g t equal to minus sin alpha pi over pi d over dt. So, we are making use of this solution to arrive at the solution of this equation. Let us see how we get. Okay, so, f s is equal to, when f s is equal to integral over s to b gt dt divided by h t minus h s to the power alpha 0 less than alpha less than 1. When we have this integral equation where h2 is a monotonically increasing function, then the solution is this gt equal to, then the solution is gt equal to minus sin alpha pi over pi d over dt integral t to b h prime u f u du divided by h u minus h t raised to the power 1 minus alpha. Now, let us compare. So, our integral equation is this. We want to know the function g t. We want to solve this equation, means we want to know the unknown function g t. So, and this is known function. We can divide this known quantity by c pi cosic alpha pi, and then the left hand side will be integral u to 1 t to the power 1 minus alpha g t over t minus u to the power 1 minus alpha t minus u to the power 1 minus alpha dt. So, when we compare with this, what we notice is that here we have, in place of s we have u here, and so hs is nothing but hu. Hu is equal to u, ht equal to t. When ht equal to t, it is a monotonically increasing function because h prime t is equal to 1. So ht is strictly increasing, and so we can apply this solution of this integral equation. So what we have is integral u to 1 t to the power 1 minus alpha gt dt upon t minus u to the power 1 minus alpha. When we compare with this, in place of in place of s we have u, and in place of b we have 1 here. So what we have, in place of gt here we have t to the power 1 minus alpha gt. So we will have this solution, t to the power 1 minus alpha gt. We can have lambda also, this lambda also together with this unknown function. So lambda times t to the power 1 minus alpha gt is our unknown thing. So we can say lambda times t to the power 1 minus alpha gt, and then we can divide by this quantity pi cosec alpha pi here on the right side. So then we will get sin square alpha pi upon pi square d over dt of then integral t to 1, because b is 1 here, and then h prime u is equal to u, so h prime u is equal to 1. So then we have du, in place of fu we write this function, the known function, and then we have u minus t to the power. Here we will have here we had alpha, and but here we have 1 minus alpha. So alpha will be replaced by 1 minus alpha, and therefore we have here u minus t raised to the power alpha, because in the solution alpha will be replaced by 1 minus alpha. So this is what we have, and then c sin alpha pi over pi times 1 minus t to the power alpha. So then we can write it further as lambda times t to the power 1 minus alpha over into gt sin square alpha pi over pi square d over dt of integral t to 1 0 to u minus t raised to the power minus alpha u raised to the power u minus s to the power alpha minus 1 s to the power 1 minus alpha fs ds du 0 to u minus t phi su. We are putting the value of phi su here. So when we put the value of phi su and combine the two integrals, we have this. So phi su we are putting, phi su is equal to 1 over u minus s to the power 1 minus alpha s to the power alpha. So we are putting that value and arrive at this solution of the integral equation, Cauchy integral equation of second kind. Now we can further write it as, since cot alpha pi equal to minus lambda pi to the power minus 1, sin alpha pi is equal to lambda pi over under root 1 plus lambda square pi square. So this equation, this equation can also be rewritten as this, lambda t to the power alpha minus 1 over 1 plus lambda square pi square d over dt of this integral plus c over t to the power 1 minus alpha 1 minus t to the power alpha under root 1 plus lambda square pi square. So so this is the solution of the Cauchy integral equation of the second kind. Now let us take in now here in the limits of integration in the Cauchy integral equation we have taken to be 0 1, but they can be replaced by the real numbers a and b. We will define the translation and scale expansion the way we defined in the case of Cauchy integral equation of first kind. We will write t dash equal to t minus a over b minus a and s dash equal to s minus a over b minus a, and we will get the solution for the case where the in the integral equations the limits are a and b instead of 0 and 1. Now let us consider this integral equation, Cauchy integral equation of second kind. So gs equal to s plus lambda times integral 0 to 1 gt dt over t minus s. So in place of fs we have s here. So fs is known to us and we want to know what is the unknown function g. So let us go back to the solution. This is the solution of the Cauchy integral equation of second kind where fs is known function. So replace fs by s and then we have s to the power 1 minus alpha. So, we will be getting s to the power 2 minus alpha. So, we replace the value of f s here and get the solution of the given Cauchy integral equation of second kind as g t equal to this plus this expression. With that, I would like to conclude my lecture. Thank you very much for your attention.